Good. Let's get started on our half day. Okay, so the main plan today is to tell you about one particular tool from statistical physics, the cluster expansion. I do want to start, so the last lecture was about how do you use some statistical physics ideas to prove a combinatorics theorem. I want to tell you, I won't give you the proof, maybe I'll tell you how the proof goes, but I want to give you sort of the opposite example of a couple of theorems that are really important in statistical physics, but once you see the theorem and I tell you how it's proved, you realize it's actually like an extremal combinatorics theorem. And it will also be related to complex analysis, so imaginary numbers, and those will play a very important role in what comes in the last three lectures, which maybe sounds a bit surprising because we're just talking about counting things and discrete probability. Why in the world are complex variables important? So we'll see. Good. So the story is in 1952. There's two physicists, Li and Yang, and they wrote two different papers. So they actually, I think one was the advisor of the other, and they worked together. They won the Nobel Prize, not for the amazing thing I'm about to tell you, but for some real physics. You'll see, actually, in the way that they named their theorems that there might have been some tension, and there was indeed tension throughout their lives. But they wrote two papers in 1952 about statistical physics. I guess I should have written the names in the other order. So the first paper, it was Yang and Li, so Yang came first, was about a theory of phase transitions in statistical physics models. And let's say a theory of phase transitions. And the idea was that the important thing was to understand the location of complex zeros of the partition function. So for the moment, let's just, I want to think of the partition function as a polynomial, so let's think of like the hardcore partition function or something like this. So, if you have a finite graph, this partition function, it's a polynomial of this variable lambda. Of course, when we plug in, all the coefficients are positive, and the leading constant term is 1. So if you plug in a positive number, which we want to do when we're talking about probability, you'll always get something positive. There's no 0. But it's also a polynomial, and the fundamental theorem of algebra says that if it's degree n, then there's n roots of this polynomial in the complex plane. So they exist somewhere in the complex plane, just not on the positive part of the real axis. Okay? So maybe, here's a drawing of the complex plane. Maybe you have some negative roots. Maybe you have some complex roots that appear in pairs, and things like this. And what the Yang-Li paper says is to understand where possible phase transitions are in the positive real axis, where you care about, you need to understand zero-free regions in the complex plane. So what do I mean? I mean, let's say here's some region in the complex plane that includes part of the positive real axis. And remember, I'm thinking about my computing the pressure or something, taking some sequence of boxes in Z2. And a zero-free region, I mean a region in the complex plane so that there's no complex zero for any of these graphs. So a uniformly zero-free region. Okay? And if you have a uniformly zero-free region, let's say that goes up to, I don't know, lambda 1, then actually the pressure has to be analytic from 0 to lambda 1. Okay? And this is just follows by complex analysis. So one useful thing today will be to write the following. Z of lambda, it's a polynomial, so we can write it in terms of its roots. It's the product from j equals 1 to capital N. Here's n is like the, I guess for the independent set case, it's the size of a max independent set. So it's the degree of this polynomial. 1 minus lambda over rj, where rj's are the roots. Are the roots. Okay, and what are we interested in with the pressure? We're interested in like 1 over volume log z. Okay, so we can take a log here, log z of lambda. Well, this is nice. It's the sum of the log of 1 minus lambda over rj. Okay, and the point is that if lambda is not close to a root, okay, if lambda, if you plug in a root here, then it's bad. You're taking log of 0 and it blows up. But if you're bounded away from a root, then the log is bounded. And so then log z is proportional to n. And the number of roots, the size of the max independent set is proportional to the number of vertices in the graph. And so actually, if you are in this zero-free region, if you're strictly inside, let's say, then this finite volume pressure, 1 over volume log z, is bounded. And then there's a nice theorem in complex analysis. Okay, I'm not an expert in complex analysis, but I think it's Montel's theorem, that says if you have a sequence of analytic functions, so log z when it's just a finite graph is an analytic function. If you have a sequence of bounded analytic functions, the limit is an analytic function. Okay, so this this is just complex analysis, but this is a really important idea of Yang and Lee, that if you have a zero-free region, you can't have a phase transition. Or the other way to say that is, how do you have a phase transition? To have a phase transition, what you need is, as your sequence of boxes or whatever graphs get larger and larger, you need to have complex zeros that condense, that approach the positive real axis. That's the only way to have a phase transition. We know there can't be a zero on the positive real axis, but if you have a phase transition, you're going to have a sequence of complex zeros that approach. So zeros condensing to the positive real axis. So this is the first of their two papers in 1952, sort of setting out this program of understanding phase transitions via complex roots. I still find it kind of amazing because, like, we're talking about positive things, probabilities, and complex analysis plays such a big role. So any questions about that sort of framework? Okay, good. The second paper they wrote in 1952, the Li-Yang paper, so now they reverse the order of the names. And this is one of the theorems that I think of as like actually a combinatorics theorem. So they're thinking about the ferromagnetic easing model. And so I'm going to write the partition function with two variables now. So you'll have beta, the inverse temperature, and also you'll have a lambda. So we want to think about biasing configurations towards plus or minus. So we're going to sum over all configurations, lambda to the, let's see, size of sigma, just sum up all the coordinates. Okay, so if lambda is bigger than 1, you're favoring plus. If lambda is less than 1, you're favoring minus. If lambda is 1, then it's symmetric. There's no bias. And then e to the beta, let's say, number of monochromatic edges. Okay, so this is the easing model. It's the same easing model as I introduced on the first lecture, except there I didn't have the lambda. I just thought of lambda equals 1. And if you think of beta being fixed, then you can think of z as a polynomial in lambda. And the theorem is the following. For every g and every non-negative beta, the following holds. Zg beta lambda is not 0 if absolute value is not 1. Okay, so now we're thinking beta's this fixed, yeah?
Beta or minus beta in this?
Positive beta, I'm saying this is monochromatic edges. So I sort of put the minus in two places, yeah. Okay, so we're thinking of beta being fixed. We're thinking of z as being a polynomial in a complex variable lambda. And what this theorem is saying is the only possible complex roots are on the unit circle. Okay? And the reason I say it's a combinatorics theorem is, you know, what they were interested in is actually saying something about the phase transitions in the Ising model on ZD. But if you tried to prove this theorem for like grid graphs, I think you'd be completely lost. The important point of the theorem is it holds for every graph. And this is really like what we do in combinatorics. We prove things for every graph, extremal things. And the proof, you know, one of the nice proofs goes by induction. You start with the base case of an edge, and you work your way up. But yeah, so what it says is basically, what's the physical meaning? If lambda is not 1, so if lambda is, you know, less than 1 or bigger than 1, you can't have a phase transition, because the only place that zeros could possibly condense would be at lambda equals 1. And this intuitively makes sense, right? Because there's some, you know, if you're biased towards plus or biased towards minus, you don't expect to see this coexistence of plus and minus Gibbs measures. But the theorem is very, very strong. It says for every graph. Questions here? Yeah, so this is a nice sort of application of their theory. I want to tell you one more theorem in the same flavor. And this theorem is about something called the monomer-dimer model. And the monomer-dimer model is a probability measure on matchings of G. And let's say mu G lambda of M is lambda to the number of edges in the matching over ZG. Let's write match just so we don't get confused, of lambda. Okay, so you're picking a random matching, not necessarily perfect matching. So in particular, like the empty set of edges is a matching. And you're picking a matching with probability proportional to lambda to the size. So this is really like the hardcore model, but for matchings. In fact, it is the hardcore model on the line graph of G. The line graph is where you take edges and vertices and swap them. But this is a nice measure on matchings. And you know, you can ask, you know, about phase transitions and all the questions we've asked. I think if you just look at this, if this is the first time you've seen it, I don't think you might think it's that different from the hardcore model on independent sets. It looks a lot the same, but it turns out it's very different, and it's different in this sense. So this is a theorem of Heilman and Lieb. And I think this is from like 1972. And again, it's going to have this combinatorics feeling. And the theorem is for all graphs G, all the roots all the complex roots of the matching polynomial are negative reals. So the picture looks a lot different than the Ising model. For any graph, the only roots you're going to have for the matching polynomial are negative real numbers. So the matching polynomial is a real-rooted polynomial. Okay, so use your knowledge now. What does this mean about phase transitions in the monomer-dimer model? Yeah, someone shook their head. That's correct. So the monomer-dimer model has no phase transition. So even though it looks a lot like the hardcore model, and we do know that the hardcore model on like ZD has a phase transition, on no infinite graph does the monomer-dimer model have a phase transition. Because you can't have zeros condensing onto the positive real axis. So it's a cool theorem. It actually says a lot more. Maybe I'll just give one other consequence of this. And there is, I think if you do a little bit of looking, there is a way to prove the Heilmann-Lieb theorem and the Li-Yang theorem in one proof, which is nice. But another consequence is corollary. The random variable let's say x equals the size of the matching drawn from UG lambda for any graph, has the distribution of a sum of independent Bernoulli random variables. So you have this random variable that counts the size. I give you an arbitrary graph. You have this random variable that counts the size of the random matching. You know, a lambda can be anything. And what I'm saying is it equals in distribution the sum of independent Bernoulli random variables. Kind of amazing. The number of these Bernoulli random variables, at least we know, it's the size of the maximum matching. It doesn't tell you right away what the parameters, these are not IID Bernoullis. They might have different parameters, but it's the sum of independent Bernoullis. And what this means is that as long as you know maybe that the variance of this random variable tends to infinity, then say it's asymptotically normal. Because you can do everything you know how to do for independent random variables, you can do here. Why does this follow from this theorem? It's because, and maybe this is a good exercise, but once you rewrite things a bit, this partition function is the probability generating function of that random variable. And what we're saying is that when it's real rooted, we're saying that z of lambda, again, I'm writing this again, but it's a product of 1 minus lambda over some negative number. One of these is actually the probability generating function up to some scaling of a Bernoulli random variable. And so, you know, and what's the probability generating function of a sum of independent random variables? It's a product of their probability generating functions. And so the theorem is telling you the form of the probability generating function. Yeah. Okay, good. So these are two famous theorems. They're very important in statistical physics. They really constrain the possible phase transitions in these two very special models. But you know, in some ways, these two models, the ferromagnetic Ising model and the monomer-dimer model, they're really nice. We really sort of know a lot about them, know about their phase transitions or lack of phase transitions. We also, you know, back to algorithms, I'll just say as a side note, there are efficient algorithms for sampling or for approximate counting, for ferromagnetic easing, and monomer-dimer models for all graphs. Actually, both of these theorems are Markov chain algorithms due to Jerram and Sinclair. But just to say that we have these really nice theorems about the zeros, but also from a very different perspective, these two models are very nice. But the models that we're going to talk about for the rest of this course are not going to be as nice. They're going to be nice in some regime of parameters, not nice in other regimes of parameters. And so we're going to have to do a lot more work to understand them. Yeah.
Sorry, probably a silly question. Do we have a combinatorial consequence of the axis of these transitions for the monomer model?
What kind of combinatorial consequence?
I don't know, like, because you said, you mentioned from the statistical physics point of view and now from the algorithms one, but you didn't say anything about it.
Yeah. There is. It's not a corollary of this. You have to do some work. But one interesting thing about monomer-dimer model is the number of matchings of a sequence of graphs that's Benjamini-Schramm convergent to another sequence is approximately equal. So, but it's the same. It's really the same phenomenon. So the number of matchings of a graph is like locally determined. And something with a phase transition can't be locally determined. Yeah, very good question. Okay, good. So we will move on. And I'll give a little preview of what we want to be thinking about before I introduce the next stuff. So hopefully, the one thing I hope you have gotten so far is that in combinatorics, in statistical physics, in algorithms, we really care about estimating z. Okay, so that's really where we are, and now we need some techniques for estimating z, and that's what the rest of the course will be about. Where we're headed is the following. Actually, I think if you read the title of my course, I said something about large deviations in random graphs. And I haven't said anything about large deviations in random graphs. So let me say something about that. Let's think about G and P. We've heard this this week. And let X be the number of triangles in a random graph. What I want to know is, or what I want to estimate is what's the probability in G and P, so P is the subscript, that X is 0. What's the probability you're triangle free? Let's just write this for a second. It's sum over all triangle free graphs. And what is it? It's P to the number of edges of G, 1 minus P to n choose 2 minus the number of edges of G. Okay. I can pull that 1 minus P thing outside. And 1 minus P to the n choose 2. And then I'm going to write this sum over triangle free. Okay, I'll make some notation. T is triangle free. Lambda to the number of edges of G, where lambda is P over 1 minus P. But then I can just define this sum. Oops, this is times. I can just define this sum to be z of lambda. This looks a lot like a partition function, right? Sum over some set of objects, lambda to the size. What is this actually? This is the partition function of the hardcore model on a certain 3 uniform hypergraph. Right? So the hypergraph, the vertices of the hypergraph are all the n choose 2 edges of the complete graph. and you get a hyperedge if you make a triangle. And so an independent set in this hypergraph is a set of edges of the complete graph that make no triangle. That's exactly this object. So really our task is going to be understanding this partition function, or the logarithm of this partition function. There's a Gibbs measure associated to this partition function, and that's exactly the conditional measure of GNP, conditioned on the event of no triangles. So this is where we're headed. We want to understand this. The hardcore model is much more complicated than the two nice models we have there, and as you might imagine, knowing something about combinatorics, things get way more complicated when you go from graphs to hypergraphs. So this is not an easy object to understand. We're going to need some tools, and we're going to have different strategies depending on what the value of P is. But just to say, this is where we're headed. Good. Okay, so I want to introduce the cluster expansion today, and then we may have time for an application, or maybe next time we'll start with an application. And so the place I want to start is something called the ideal gas law. And what I want to imagine is, I'll talk about maybe like the simplest model of a gas. You have a big box, and you have a bunch of particles that are the molecules of the gas. And what is an ideal gas? It's just a gas where the particles don't interact. Okay? And so what is the partition function of this ideal gas? Well, you sum over the possible numbers of points, lambda to the number. So it's just like, we have an activity parameter just like we did in hardcore monomer dimer. And we should have over k factorial for the orderings. And we integrate over this box, capital lambda. Okay, so what is the value of this? Well, it's sum from k from 0, lambda to the k, volume of the box to the k over k factorial. And this is e to the lambda volume. Right? So this is, does anyone know what distribution the points have if this is the partition function? So what are non-interacting points? What's the nice distribution? It's a Poisson process. So this is a Poisson process. And the density, okay, so this is our partition function. The density, well, the density of a Poisson process, let's call it the density rho. It's just lambda. And the pressure, remember what the pressure is. It's 1 over volume log of the partition function. The pressure also is just lambda because you take a log and you divide by the volume. And so what is it saying? It's saying the two things that you might actually care about when measuring a gas, like two real statistics, the pressure equals the density in the ideal gas. So this is the ideal gas law. If you squint your eyes, this is the same as PV equals nRT, right? Because N over V is the density. Okay, we don't have a temperature parameter. R, I guess, is a constant. So this is the ideal gas law. Okay, but that's not such an interesting statistical physics model. What do you actually care about? You actually care about a model where when particles maybe are close together, they have some strong interaction, and when they're far apart, they have some other interaction. And what you really want to know if you're a physicist, you want to understand how the relationship between these physically relevant statistics changes from the ideal gas law when you have an interaction. And so that was the whole idea of the cluster expansion. You want to start with something you know, then add in a an interaction and see how this relationship changes. And the hope would be that if the interaction is very weak, so maybe the temperature is high or the density of the particles is very low, then the relationship doesn't change by much. It's a small perturbation of this ideal gas law, and we can measure it in some sense. And that's what the cluster expansion does. Even in that very vague introduction, there's two things to keep in mind. One is it's a perturbative technique. You start with something you know well, and you change it slightly and try to measure what happens. And the second is we shouldn't expect it to work when you get very far from what you know. Okay, and so both of those will be important. Maybe as an exercise, you could think about like a discrete ideal gas law where you have, just your graph is just a set of isolated points, and we do the hardcore model. It's very easy to calculate the density and the partition function. The ideal gas law won't be density equals pressure in this case, because there's like a hidden hardcore interaction where you can't put more than one particle on a point, but you can calculate what that is. Yeah. Okay, so how do you start to measure the changes when you have an interaction? And the idea dates back to Meyer in the 1930s and 40s. And the idea is to expand log z of lambda in powers of lambda around 0. So, I can tell you what the cluster expansion is. It's just the Taylor expansion of log z. So the cluster expansion literally is just Taylor expanding the log partition function around 0. But it turns out that the coefficients have a very nice form. And so there is a good reason to give it a name beyond just saying Taylor expansion. Okay, so that's the idea. I was considering deriving the cluster expansion for you. I did it in the notes, but I don't think it's necessarily the best thing to just see me write a bunch of lines of calculations. I'll tell you the first couple of steps, and then you can look in the notes to see what it is. And so what do I mean? Okay, so we really should have a good setting. So the setting will be, G will be a graph. And I want to generalize a little bit because this will be useful later. But the model I'll look at is a hardcore model, but with a vector lambda, where every vertex gets its own activity parameter. Okay, so what is this? This is sum over independent sets, product over v and I of lambda v. Okay, so if I set all the lambdas to be the same, then we get the same model we had before, but it will be very useful for us to look in this multivariate setting. Yeah, good. So that's the setting. And what we want to do is to derive formally, so forgetting about convergence for a second, derive formally log the Taylor series, or the expansion for log z of lambda around lambda equals 0. So the idea and the first couple lines of the derivation is to start with the partition function. And write it as like the sum over the possible number of particles. And then I think we'll have like a 1 over k factorial. We'll have, let's say, we want to choose which vertices to go there. So we want to sum over v and v to the k. And let me write it like this. Sum over v1, v2, vk, and v. Product of the lambda i's. And then we want to insist that this is an independent set and it only has k particles. And so we'll write something like this. 1 minus f of, let me write, product over I not equal to j, 1 minus the indicator that vi equals vj or vi neighbors vj. Okay, so if vi equals vj, then this becomes a 0. So that's just insisting that you pick k different vertices. And if vi neighbors vj, then it's not an independent set. And so this insists that you only pick independent sets. Now, the nice thing is that we have this product of 1 minus something. So you can actually expand the product. And so this product becomes sum over graphs on subgraphs of k, k sub k, and then product over the edges of, I shouldn't say g, let's say h, product over the edges of h of minus this indicator, ij. Okay, so you get this sum over graphs once you expand the product. And then the basic idea is that this whole thing that you're summing factorizes over connected components of graphs. And then you do some stuff, and you eventually get that this is the exponential of something. Okay, and the exponential of something, that something is the formal power series for log z. So I think you can, if you want to see the derivation, look at the notes. I'll tell you now what the form is, but the important thing is that the thing that you're going to be summing over is related to connected graphs. Okay, and if you, from some branches of combinatorics, I think this is obvious. I like when people go from like the generating function to exponential generating function, you go from big set of objects to connected set of objects. So it's the same idea. But let me tell you the form. Good. So we're in the same setting. I need to tell you what a cluster gamma is a tuple, so an ordered tuple of vertices whose ordered tuple of vertices whose incompatibility graph H of gamma is connected. So what is this graph? This graph, there's an edge if vi equals vj, and an edge if vi is a neighbor of vj in G. So you can think of this as you put an edge if there's an edge in the fully looped version of G. So for instance, like if I have, so here's my graph, v1, v2, v3, v4. a cluster, a valid cluster would be something like V1, V1, V3, V2 is a cluster. So it's an ordered tuple. I can repeat vertices, and the order matters. And if I look at the graph, well, these are joined together, these are joined together, and these are joined together. So this is the incompatibility graph is connected. Something that's not a cluster would be V4, V2, V2. Right? Because this incompatibility graph is disconnected. Okay, so that's a cluster. The Ursel function so it's a function of a graph, and the Ursel function is, okay, I want some normalization, 1 over number of vertices factorial, and sum over all subsets of the edges of H, so that V of H with A is connected. So it's a sum over connected spanning subgraphs of H minus 1 to the size of A. Okay. So it's something you can compute on a graph. This is actually an evaluation of the Tut polynomial. That's good to know. Maybe an example. What if H is a triangle? So what do we have? If we take 0 or 1 edge, we can't get a connected graph. So we don't have anything there. Any of the 2 edge pairs give you a connected graph, and you get a minus 1 squared. So it's going to be 3 for that, plus, well, you get the 3 edge thing, so you get a minus 1. Oh, and then you should divide by this factorial, right? So it's 1/3. Okay, so that's an example. And with these 2 definitions, then we can say what the cluster expansion is. So as a formal power series, log z of lambda is the sum over all clusters, this combinatorial factor for the incompatibility graph, and then the product over all the vertices in the cluster of lambda v. Okay. So this is a kind of nice thing. The really important thing is that these are connected objects. So they're not quite connected subgraphs because you can have multiple things appearing, but they're connected objects. And this is crucial to everything that's going to come. Okay, so that's the cluster expansion. We should do an example. The simplest example is just to take G to be 1 vertex. Okay? What are the possible clusters? We can call it V. What are the possible clusters in this graph? Well, you can have 1 vertex, V by itself. You can have V twice. You can have V 3 times. You can have V 4 times, and so on. So for every k, there's 1 cluster with k copies of V. And so log z, sum over k at least 1, we're going to get a lambda to the k, right, because we have this power of lambda. And then we're going to get the Ursel function of the clique on k vertices, right? Because we have this self loop, the incompatibility graph here is fully connected. Who can tell me what the Ursel function on kk is? Yeah, so hopefully you're not trying to sum over a bunch of things. The point is, you know what the Taylor series for the partition function here is, right? The partition function is just 1 plus lambda. And so this is just the Taylor series of log of 1 plus lambda. And from that, we can say what this is. So this is actually minus 1 to the k plus 1 over k. And so you get the right expansion. Sum over k, minus 1 to the k plus 1 over k, lambda to the k. Okay, so that's a very easy example. We already knew how to take the Taylor series of log 1 plus lambda. Okay, but at least you see something. I should point out right away, is there any phase transition or bad behavior of the hardcore model on the single vertex graph? No, of course not. It's just a Bernoulli random variable. But what about the cluster expansion, this Taylor series? When does it converge for this example? So it converges if lambda is less than 1. That's the radius of convergence of the log 1 plus x power series. And so the cluster expansion only converges in this fixed region, even though the behavior of the model is really, really nice everywhere. Okay, so that's an important point to keep in mind, that the cluster expansion can fail for reasons nothing to do with probability. Why does it fail, actually? Well, where's the what determines the radius of convergence of a power series? It's the nearest 0. And the 0 of this partition function is at minus 1. Okay, so this negative 0 is telling us something about the cluster expansion. Okay, one more example. So G is, let's say, an n vertex delta regular triangle free graph. And now I want to say what the cluster expansion is. So I need to look at the different types of clusters, the number of them, and the value of the Ursel function. So there's clusters that are single vertices. There's n of them. The Ursel function is 1. You can have 2 copies of the same vertex. I wrote these things down so I won't mess up. Of course, there's n of these. The Ursel function is minus 1/2. We saw that already. You also have clusters for each edge, ordered edge. There's delta n of these, also minus 1/2. You have another cluster that's 3 copies of the same vertex. You have an edge, and one of the endpoints gets repeated. You have a path on 3 vertices, and so on. You don't have any triangles because I said it was triangle free. Okay, we have n of these. This is 1/3. I wrote down 2 delta n of these. Did I write that down? 3 delta n. 1/3. Okay, the next thing is more complicated. 3n delta minus 1, 1/6. Okay, so you can see what this exercise is like. If you have a given graph and you want to compute a term of the cluster expansion, you need to do all this counting of small subgraphs, do some combinatorial calculation, but then you can start to write out the terms. And so log z, let's just assume for now we're in the univariate case, just a single lambda. What are we going to get? We're going to get, so one, let me divide by n here. So one thing we're going to get is like the contribution from the clusters that are the multiple copies of one vertex. And that's actually exactly the contribution you would get from the ideal gas. And that's this example. So you get the lambda minus lambda squared over 2 plus lambda cubed over 3, and so on. But then you get the corrections that actually come from the graph structure. And so the first one, maybe not surprising, is minus delta over 2 lambda squared. Okay, and then there's a lambda cubed term. 2 delta minus 1. Okay, so this is the first terms of the cluster expansion. But if you erase this part and remove the ideal gas contribution, these are the first and most important terms of the correction. And there's actually like a nice interpretation of removing the ideal gas terms. We can look at zg of lambda over 1 plus lambda to the n. So 1 plus lambda to the n would be the same number of vertices but no edges, the partition function. And this is actually a probability. And it's a probability we've seen today, and actually you saw in the exercises. This is the probability that if you pick vertices independently with probability lambda over 1 plus lambda, you get an independent set. Okay, and so taking the log, this is an expansion. If you remove the ideal gas terms, this is an expansion of this probability. And then maybe it's not so crazy to look at. You know, you've actually seen this before. This is the first term in Janssen's inequality, and this is the second term in Janssen's inequality. But it keeps going. There's more and more terms, and depending on your parameters, maybe 100 terms are significant, maybe 3 terms are significant. Maybe actually the answer is you need a real infinite series. Okay, so those are some examples. Let me, just in the last 5 minutes, say something about convergence. So far, we're just deriving a formula, but the big question is, does the series converge? If the series doesn't converge, then it's not going to be useful for actually computing things. If the series does converge, then you have all the tools of complex analysis and power series and things like this. You can derive a ton of information, and we'll see some of that next time. But this is the big question, and it's not an easy question, but we do have some results. And so maybe I'll end with a result of Shearer. So this is yet another paper of Shearer, different than the ones you've heard about this week. And this is kind of a remarkable paper. So it proves 2 things. I'll first say the convergence result. So if G has max degree delta, and lambda's in absolute value is at most delta minus 1 to the delta minus 1 over delta to the delta, then cluster expansion converges. and in fact, I could put a lambda v here, and if lambda v is at most this for all v, so it holds in a multivariate setting. What is this number? This is like, as delta gets large, 1 over e delta. And he also proved that if you have a set of events for a set of events with a dependency graph G. So remember, if you remember Lovász local lemma stuff, dependency graphs are not unique. Okay, so but if G is a dependency graph for this set of events, and that's all you know, then the optimal LLL condition, so the upper bound on P, is the radius of convergence of log ZG of lambda. So if you only know for your set of events that the dependency graph is G, then the best bound you can get for the upper bound on P in the Lovász local lemma is the radius of convergence of cluster expansion. It's actually it's known for hardcore that the nearest zero is a negative number. So it's the closest zero on the negative axis to zero. And he proved that if all you know about G is the max degree, then this bound is optimal. And that's where this 1 over e delta comes from. And this is actually achieved by finite truncations of the regular tree. So if you take like the deregular tree and truncate it at large depth, you'll get zeros that approach this value. So this is a really remarkable connection between cluster expansion, Lovász local lemma, statistical physics combinatorics, and Shearer's paper is like, I don't know, it's like 4 pages, and it takes you like 4 weeks to fully read. But if you want the longer version, there's a great book paper by Scott and Sokol. Book paper, I mean, the paper is as long as a book, but it goes into tons and tons of detail about this connection between Lovász local lemma, cluster expansion, how do you prove cluster expansion converges. What it doesn't go into is how do you use this to do combinatorial enumeration, and that's what we'll do in the last 2 lectures. Thanks.